Great. So hello, everyone. Thanks for coming. So today I'm going to be telling you about quantum satisfiability and how these problems can be complete for a plethora of classes, some of which are new classes. This is joint work with Alex from Perimeter Institute and my supervisor, Daniel Nagai from the Slovak Academy of Sciences. So our motivation comes from the comparison between SAT and quantum SAT. As you may know, SAT is kind of like the golden standard to study the complexity of problems in classical sciences, and quantum SAT falls a little bit short. And actually this title currently seems to go to the local Hamiltonian problem instead. For both of these problems, we can define variants based on the instance structure. So for SAT, we can define 3-SAT, XORG-SAT, Horn-SAT, and for quantum SAT, we can define variants based on the projector type, which may be diagonal, stochastic, or commuting. And now what is very interesting is that in the classical case, you can prove that all of these variants fall either in two complexity classes, P or NP complete. Now, in the quantum case, from the variants that I found that have been considered, they fall into 4 complexity classes, P, NP, MA, and QMA1. But there is no complete classification like in the classical case. So in theory, there could be other classes in there, and our work fills in some of these gaps as well. And while it might be true that quantum SAT is not as general as you would expect, our results shows that this is also very rich in different areas, and it's a problem worth studying. So just a little refresh. So satisfiability is a problem where you have a set of variables that are usually Boolean and operators and or not. And then I give you one of these, and you're supposed to answer whether there is an assignment of the variables such that the formula evaluates to true. And now I can define variants based on the instance structure. So the one that I just showed you is actually an example of 2CNF SAT, or just 2SAT, where I have my clauses, which are the parentheses. I have 2 variables in each clause, and then those ones are joined by OR operators, and the clauses are joined by AND operators. Similarly, I have 3SAT, where I have 3 variables in each clause, and HORN-SAT, where you have at most 1 positive literal in one of these clauses. And like I mentioned before, all these, different variants yield different complexity results. And this is actually, this happens for every other variant that you can think of as well. And this can be formalized by the following 2 theorems. So in 1978, Schaefer proved that every CSP, which you can think of as a generalization of SAT to on dits or bits, is either P or NP complete. And then 40 years later, Schuck demonstrated that every CSP on dits also falls within those 2 complexity classes as well. And now this is very surprising, because if P does not equal NP, which is what you would expect, then there should be other complexity classes between them. And this is also very interesting because CSPs are very general and natural sets of problems. So you would expect maybe something in between, but this is not the case. And this is relevant because these proofs are constructive as well. So yes, that these proofs are constructive. So if you're trying to determine the complexity of your problem, you can just follow these guidelines, and it'll tell you whether it's P or NP complete. And this actually pinpoints the essence of CSPs and what makes them easy and what makes them hard. And now something that is not under the surface here is that if you start with a qubit problem that is easy, and you try to reduce that to a problem in bits, then you might end up in a larger class of problems that are NP complete. So we do not have this like robust reductions for CSPs. And this is relevant for us because we show that this is actually not the case in quantum constraint satisfaction problems. And we make use of this result in a later part of the talk as well. So keep that in mind. So now, due to the success of SAT, I think it made sense to define quantum SAT. And this problem is defined as follows. So given n qubits or qubits and a set of k local projectors, where by k local we mean that out of these n qubits you only act on k qubits at a time, you're supposed to determine whether there is a state in the null space of all of these projectors, or the energy, which you can think of as an energy penalty for not satisfying these projectors, that is greater than the inverse of a polynomial. And you're promised that one of those 2 is always the case. Now, for the physicists out there, so if I define a Hamiltonian as a sum of these projectors, then this is equivalent to asking whether the Hamiltonian is frustration free. Now, in terms of qubits, we have that 2 quantum sat is in P, it's easy, but 3 quantum sat is QMA1 complete. And here, QMA1 is a variant of QMA, so meaning probabilistic verification with a quantum computer, but with perfect completeness, where by that we mean that if we have an instance for which we are supposed to say yes, then we accept that instance with certainty. And it is not trivial to show that QMA1 is equal to QMA, and as Stacy pointed out yesterday, you can only get super exponentially close to 1, but not exactly 1, we believe. And also perfect completeness is quite tricky here, because if you have 2 classes with perfect completeness, it is not known whether those 2 are equivalent under different gate sets. But there was a really nice paper by Dorian Rudolph last year that alleviates this problem for the classes we consider here. And that's all I'm going to say about this anymore, and then I'm going to forget about those classes. So if you're interested in the details, you can go and check the paper. All right. So again, we can define variations of this problem. And here you have several options. So you can do it based on the topology. So you can restrict your interactions to act on a 2D lattice or whatever. And then you have mixed qubit dimensions or extra promises. And there's been a lot of really interesting work in these settings as well. But for us, this is too restrictive. So for an actual comparison for Schaefer and Shook's theorems, we require that the projectors must be from a finite set, S, which may be of a type, like I mentioned before, diagonal, commuting, stochastic, or just an arbitrary finite set. And for those familiar with the literature, the problem is known like that. And before our work, as far as I could find, all of these variations fell into those 4 boxes. But like I mentioned before, we don't know if there were more. And we started wondering why this may be, whether perhaps the dependence on the gate set spooked a lot of people, or perhaps maybe just people weren't interested in this problem as they were interested in the local Hamiltonian problem. And then it occurred to us that we perhaps could put one extra problem in that category. So for our results, these are the 4 complexity classes that I mentioned before with complete quantum sat problems. And our main theorem states that there are quantum sat qubit problems that are complete for an additional 9 classes, 6 of which are new. So the star of the show is SLCT quantum sat. Very catchy name, I know. And we showed that this problem is BQP1 complete on 4 local clauses on 6-dimensional qubits, or 48 local on qubits, which this relates to the result that I mentioned before, that we can translate from qubits to qubits now. So initially, we just wanted to prove that problem. But then we realized that by performing modifications on this problem, we could get a CoRP complete problem and a QCMA complete problem as well. And then we realized that we could combine these problems on the left column with the ones in the middle to create new problems that are complete for new classes as well. So here we're combining 3-sat and classical SLCT quantum sat with something we defined and called the direct product of CSPs. And we showed that this is complete for a class that also combines those classes where those 2 come from. And similarly, we defined a direct sum, and we proved that those ones are also complete for a slightly different class, and 2 other pairs. So for a total of 6. And now we can combine, I'm going to describe a little bit, sorry. So yeah, I'm not gonna really talk about those operators here. I'm more interested in discussing the classes themselves. And there's many different ways in which you can combine 2 classes. So the first one is the pairwise intersection, where you have that this is the class of languages where the problems are themselves the intersection of a problem, one in A and the other one in B. Or more hand-wavy, the problems that can be solved by checking a property in A and a property in B at the same time. And an easy example of this is sat on sat. So if I give you 2 formulas, phi and psi, and you can think about them as 3 CNFs, then you're asking whether the first one is sat and whether the second one is unsat. And this is in the pairwise intersection of NP and co-NP. Why? Because the first one, I can just perform a check to see whether it's in sat. And for the second one, I just check whether it's unsat. The first one is in NP, the second one is in co-NP. And that way I can completely decide that problem. Then a different way is the pairwise union. So here, these are the problems that are solved by checking if in A or in B. For an easy example, I just give you a graph, and you're supposed to decide whether the graph is three-colorable or does not have a Hamiltonian cycle. And that is in the pairwise union of NP and co-NP. And lastly, we have the star of pairwise unions that combine that and that together. It is actually quite difficult to describe that formally, but you can understand it as a CNF formula made from problems L1 and L2. And for example, here, I just give you a bunch of these graphs, and you have to decide whether all of them are three-colorable or not Hamiltonian cycle. So this is in SOPU, NP, co-NP. And so you can say that if I try to answer that question, that is equivalent to answering that bottom question as well. So that's what we mean by that this is a CNF, kind of. All right, and these ones are just kind of like very boring examples that don't really say too much. But if you're interested in looking at these further, you can look at critical graphs that combine these ideas in a very nicer and funner way, and also the Boolean hierarchy as well. All right, so now you're ready. Oh, what happened? Ah, yes. So I want to point out two facts here. So PI and PU have been studied before for NP and co-NP, like I just showed you. And before our work, we knew 4 classes with complete quantum SAT problems. And the operators that we defined are really nothing crazy. So the direct sum and the direct product, I mean. So why are there only now new complete problems for PI and SOPU? And why only 6? Before we had 4 here and 3 there. So in combining those should have been 12, but we only get 6. So why? And this is because of the relationship between the classes that I just mentioned. So if A and B are incomparable, then we have that the pairwise intersection of A and B contains A and B, and that is all contained in SOPU. But if A is contained in B, then all of those just collapse to the biggest class, which is B. So to answer these questions, before we had that the 4 problems had those relationships. So any class that you could think of SOPU and PI would just end up in the same trivial class. So it didn't bring anything new. But right now we have that we don't know whether co-RP is contained in NP, NP and BQP1, and MA and BQP1, and vice versa. So we have one pair of classes, one pair of problems for each one of those classes. So now you're ready for the most interesting thing, I think, maybe for many of you, which is the relationship between those 13 classes. So the ones in white are the ones that existed before. Then the ones in purple are the ones, the big 3 problems, and the ones in green are the ones that spiraled from that. And now what is interesting here is that we now have these relationships in the language of quantum CSPs. And like I mentioned before, these are perhaps more general or more natural. So it would be interesting to see if having these in the language of quantum CSPs apports anything new, and we can determine new relationships or inclusions or whatever for these classes as well. And just to mention a few that we have included due to our results is, for example, P versus co-RP. And this is the question of whether algorithms with perfect soundness, with imperfect soundness can be made perfect. Oops. Or QMA and QCMA, which is whether classical messages are as powerful as quantum states for verification. And finally, something a little bit more concrete is, for example, if you prove now that any of those 2 neighbors are not equal, then that would imply that NP is not the same as MA. All right, so, and you can think of our results in 2 ways. Whether this is perhaps motivation to search for a classification theorem, or perhaps an indication that this is just too difficult. So in the first case, a future classification theorem analogous to Schuch's dichotomy theorem, but for quantum SAT, and if it has less than 13 classes, then it must mean that some of these classes are equal. Or perhaps there's an indication that this is just too difficult, which is also valid. But we raise the question of whether all of these classes exist for smaller k and d. the worst we do is 5 local on 8-dimensional qubits. So we don't know if this collapses as we put a smaller locality in smaller dimensions. All right, so besides these, we now have new solvable quantum sat problems, the CoRP and BQP1 complete problems, and the first natural BQP1 complete problem. And also, again, to reiterate, this is just a contrast with classical CSPs, where the landscape was very simple, even in the case for large dimension and large locality. All right, so some of the open questions that we have is that we should definitely keep exploring PI and SOPU. Like what other problems, what other non-trivial problems are in these classes? And perhaps even more technically, whether something like this, whether if I have that PI of AB equals PI of AC, does that imply that B equals C? And as I will tell you in a little bit, the projectors that we construct for these problems are really artifacts that we get for to get what we want. So could it be possible that we get more natural set of projectors that are complete for those classes? Finally, also perhaps showing that BQP1 is equal to QMA1, BQP1 and QMA1 are equal to their bounded side error, which is true for QCMA and QCMA1, could elevate our results and put those on par with the local Hamiltonian problem. Finally, could there be more classes with complete quantum sat problems? And the answer is we think so, and we're working on it. So we're working on it, and we have complete problems for the Fourier hierarchy, which here we mean that you have access to Hadamard layers and classical computation, and you can interleave those. And we have complete problems for every step of the Fourier hierarchy, and as well as we can define QMA versions, well, like analogs of QMA versions and QCMA versions as well, all with perfect completeness, of course. And moreover, is that PI and SOPU equip the set of classes with complete problems with an ordered semi-ring structure. So what we mean by that is that we can see PI and SOPU as product and sum operators that can act on classes. And as long as those classes have complete problems, then you can perform a bunch of these like product and sums, and you will get a new complete problem, obviously within the semi-ring properties. Now, in the remaining minutes or so, I want to tell you a little bit about the BQP1 construction. The starting point is the quantum sat QMA1 hardness proof of Ravi. So here the goal is to encode the verification circuit of a QMA1 problem into an instance of quantum sat. Such that for any instance X, I have that if it's a yes case, then our Hamiltonian, which is just the sum of projectors, then it's frustration free. And if it's a no, then the Hamiltonian has no small eigenvalue. And this is solved via the circuit of Hamiltonian transformation, where if this is my verification circuit, that I'm just saying, for simplicity, acts on 2 ancilla qubits and 2 witness qubits, and my circuit is has capital T gates, and then given an instance X, it can decide whether this is a yes or a no case. Then what you get from this transformation is a Hamiltonian acting on a logical and a clock subspace that encodes that computation. So to be explicit, we have 2 terms, P in it, that pretty much say that at time t equals 0, then those 2 qubits should be initialized to 0. Then we have capital T, propagation projectors, that pretty much keep the computation going forward. And finally, we have a single P out projector that says that here at the measurement, we want that to be 1. And now consider that funny looking state, which actually encodes all of the steps of the computation in even superposition. And this meets 3 properties. So by default, without caring about the actual input, whether it's a yes or no, we have that the init and prop projectors are immediately satisfied. And it's not super hard to prove that. And secondly, we have that P out is satisfied if and only if this circuit produces 1 there, which is what we designed it to be as well. And lastly, in this particular case, we have that if it's a yes instance, then the history state is the unique satisfying state, which is also the unique ground state. And then that covers the first case. And then if the instance is a no, then our quantum sat problem will one can show, it's a little bit complicated, but one can show that this has no small eigenvalue. Now here, we're just gonna do the same, but just in a graphical way, since it'll be more useful. So here, this is our quantum sat instance, where we have the circles are the clock particles, the triangles are the data particles. And then this chunk just encodes the initialization. Then these ones are the witness qubits. And an important thing here is that those ones are not initialized, so they remain free. So keep that in mind. I don't have these like dotted lines connecting to those ones. And then this is just the propagation. And then that is just the measurement. All right, so the main idea of our construction is that we want a quantum sat problem defined with those projectors. And it's important that, that the unitary gates are chosen from a universal gate set such that we can prove, such that we actually get BQP1 hardness. So then this problem is BQP1 hard because we can play the same game that we were doing before with for QMA1. So we have our circuit and we can encode that into an instance of quantum sat, where now notice that now those qubits are initialized. Those those qubits are initialized. And now the question is whether a problem like this is in BQP1. So now we're playing a game where I give you a bunch of qubits, and then I will apply a polynomial number of these projectors randomly on those qubits. And then you're asking whether that has a satisfying assignment. And the answer is yes, if we get that instance. Why? So those are the three properties that I mentioned before. And the proof is that 3, 1, 2. So for number 3, we have that this is the best candidate state, that the history state is the best candidate state. 1 is that the P init and P prop projectors are just immediately satisfied, like I mentioned before. And then that only leaves out the P out. And that is satisfied if and only if the circuit acting on this input produces 1 there. Which means that we can actually verify this in a quantum computer. We can just run the circuit, measure, and see if it's 1 or 0. And that'll actually help us determine whether that quantum sat instance is satisfied or not. If it is a yes instance, we will measure 1 all the time, which is what we wanted for BQP1. But if it's a no, then remember that quantum sat problems come in with a promise, that the energy is greater than the inverse of a polynomial. So then this implies that we will measure 0 with not so low probability. So if we repeat this algorithm multiple times, we will eventually be able to detect whether we are in the yes case or in the no case. But obviously, not every instance that I can generate in this way will have that nice form. So we run into some trouble, which is wacky instances that we might get as input. And these ones are very hard to interpret as a quantum circuit. So we might have like multiple initializations, and overall it doesn't have the meaning that we want it to. And the second problem is that we might get QMA hard instances as input. So those ones with free qubits lying about. And actually claiming that we can solve this in BQP1 would imply that BQP1 is actually QMA1. Yeah. So we cannot do this. Instead, what we do is we define a new quantum sat problem with projectors pi init, pi prop, and pi out. We can actually solve. And those projectors will be similar in spirit to the ones we saw before, except now we will insert new constraints to avoid problematic instances. So in the first case, we solve the first one, for example, by demanding time linearity. So here we will create additional subspaces and demand that they are maximally entangled. So my clock particles, I will add two two-dimensional subspaces CA and CV, and a new endpoint particle. Don't worry too much about that one, but I will demand that the CB subspace is entangled with the CA subspace of the following clock particle. And it is not so hard to see that this is the only configuration that wouldn't yield a violation of monogamy of entanglement. So if I flip this arrow one to the left, then the CA subspace, which is two-dimensional, would be entangled with this CB and that CB, and we cannot have that. So in this sense, we can determine these instances just classically by looking at them. And in the second case, we want to prevent free logical qubits. Like I mentioned before, those ones are quite problematic. So we solve this by defining an undefined logical state. And we will tweak the propagation projectors such that if this logical qubit is not initialized, then it is trivially satisfied. So take, for example, that instance, and suppose that I'm only acting on this free qubit at that point. Then, because that projector I can now satisfy, then there will be no longer anything demanding that I continue with the computation. So then that has a satisfying state that we know a priori, which is the history state, and on that part, and then just the trivial state on the remaining part of this chain. And now what is crucial here is that the measurement at the end won't trigger, because I can just satisfy that trivially as well. So pi out is satisfied, and as before, I mentioned before, the history state satisfies everything, the pi init, pi prop projectors, not pi out. But in this case, that is trivially satisfied, so I can decide this classically. So my algorithm is then as follows. There is a classical part that just goes over the structure of the instance and rejects on accept. So if the instance is trivial, like I mentioned before, we accept. And if the clock component is not linear, so it violates monogamy, we reject. And then all instances will now be of the desired form that I mentioned before, like linear is acting all nice on my logical qubits and whatever. And then my quantum computer will just execute the circuit that it sees on the instance. And then if one of the outcomes is 0, then we just reject. If it is 1, we continue. And then at the end of the algorithm, if no rejections occurred, we just simply accept. So for the core P proof, so that completes what I just wanted to say about that. And now just a brief description of the remaining parts of the paper. So for the core P, we have just a reversible circuit with the inputs are just random states. So then I can play the same game that I did before, but now I will just add a new term that instead of initializing these to 0, it also allows me to initialize those to the plus state. So that's where I get my randomness. And then I have a reversible circuit there, which now I have pi prop of R. So that follows through quite easily. And then for the QCMA part, I will have free qubits as well, but then I will try to enforce a constraint that pretty much acts as the swap trick that you see in often cases to demand that the witness is classical. And then for the second part, for the reduction to qubits, we show that if you can decompose, or well, we showed that by decomposing a qubit into a lot more than a log d corresponding qubits. And then we will use those extra qubits to entangle all those together. Like in a similar way like we did with in the case that I just explained. And lastly, for the PI and SOPU, all there is there, the difficulty is just to show that the sums and product of quantum CSPs retain the completeness properties of its constituents. And that's it. Thank you.
So we can take a couple of questions.
So you said one of the surprising thing about Schaeffer's dichotomy theorem is that you don't see anything between P and NP complete. So in the classical version of the problem, you don't see anything between P and NP complete. And here you see a whole bunch of classes between P and QMA1. But you also see some classical classes here, like co-RP. Is there some intuition for why co-RP doesn't appear in the classical set, Schaeffer's theorem, but it appears here, even though it's a classical class? It's not quantum. Like I understand that a quantum class cannot appear in Schaeffer's dichotomy theorem, but why does co-RP appear here?
Okay, I think that the simplest answer is I don't know. But there were several interesting results that, for example, you have that the stochastic the stochastic quantum satisfiability problem, or the quantum local Hamiltonian problem. I don't remember, but Aharonov and Grillo showed that this problem was like, I think, which one was it? The MA complete. Yeah. It was MA complete, and they showed that this is actually equivalent to a combinatorial optimization problem. So don't have any intuition why this actually appears there, but we can think about applying a similar technique to our problem and see whether there is an actual equivalent to that as well.
Thank
you. Wait, but also core P is not contained in NP. So there's that too.
So I think we can take one more question. We have one minute.
Chose two classes at a time. That is, for proving the plethora of classes, you took two at a time and taken this different new classes also. Suppose you had chosen three, would it be too difficult? And three at a time, unions and intersections and of three different classes, and try to prove the same thing. That is one main question that comes to me.
Do you mean about, because we have complete problems for
Correct.
PI and
Correct.
SOPU,
Correct.
but not PU?
Right.
Is that what you mean?
Right.
Ah, okay. Yeah, so the reason is that we tried, but the operation that we defined as the direct sum doesn't really agree with the definition of PU. And we don't know how to do it, but it could certainly be possible. Yeah, but we just don't know.
Another thing is about the D Q dits spread into greater than log D, which you used in your proof. So if it is some kind of a symmetric combination of qubits or some other classes of qubits, would it help you? That is there any specific kind of D into log D kind of qubits, basically?
Yes.
So if it is completely symmetric or some other different symmetric classes, would it help you in splitting the D into different qubits is what I mean.
So I don't
So
think I
but-
understood the question. Sorry, like it was hard to hear, but we can talk later if you want.
Okay. Thank you so much for the talk.
Yeah.